This is a revision video for the forces topic of GCSE Physics or Combined Science. I teach the AQA syllabus, but you may find this useful for Edexcel or OCR as there is a lot of common content. Since 40% of the marks in the GCSE Science exams are for the recall of key facts from the specification, this is an opportunity to check that you've thoroughly learned them. Download the worksheet from the description below, quiz yourself, and then use this video to check your answers. The first part of GCSE Physics forces is all about scalar and vector quantities. So the difference between a scalar and a vector is that a scalar only has magnitude, whereas a vector quantity has both magnitude and direction. On a force diagram, we represent forces using arrows, and it's the length of that arrow which shows us the magnitude of that. A force is a push or a pull that is experienced by an object when it's interacting with another object. Forces can be split into contact and non-contact forces, and the difference is that for a contact force to work, two objects must be touching each other, whereas a non-contact force may exist where the two objects are separated. That doesn't mean that as soon as the two objects are touching, a non-contact force turns into a contact force. So for instance, magnetic force is a non-contact force. You can feel that magnetism between a magnet and a magnetic object even when they're not touching each other. But when they do touch each other and stick together, magnetic force is still a non-contact force. It's a property of that particular kind of force, not of the fact that the objects are or aren't touching. Contact forces include friction, air resistance, tension, and normal contact force, which is the force that's experienced when one object pushes on another and then that object is pushing back. Non-contact forces include gravitational force, which we often refer to as weight, electrostatic force, and magnetic force. Force is always a vector quantity because a force always has a direction associated with it. The force that is experienced by an object due to a gravitational field acting on it is gravitational force or weight. The two factors that determine the strength of that gravitational force are the mass of the object, so in other words, if an object has a greater mass, it experiences a greater weight, and also the strength of the gravitational field. So in other words, if you're on Earth, you experience a greater weight than if you were on the Moon. The equation that connects all these things together is that weight equals mass multiplied by gravitational field strength. Weight is a force, so its units are newtons. Mass is measured in kilograms, and gravitational field strength is measured in newtons per kilogram. On Earth, the value of that gravitational field strength is 9.8, and we can measure the weight of a particular object using a calibrated spring balance, although this is more normally referred to as a Newton meter. The idea behind a resultant force is that we can take all of the forces that are acting on one particular object and sort of summarise them in a single force that would have the same effect. So for instance, if you look at my box here, I've got a force of 50 newtons to the right and 10 newtons to the left. And that box will move in exactly the same way as another identical box that just has one force of 40 newtons acting to the right. So we would call that single force, the 40 newton force, the resultant force. It's the overall summary of all of the other forces. If you have two forces that are acting in a straight line, then we can find the resultant force by adding or subtracting. So for instance, here I have another box with a force to the left and a force to the right. Because they're going in opposite directions, I would subtract these, and my resultant force would be 10 newtons to the right. Whereas this box has two forces that are both acting in the same direction, so therefore we would add them together. So this would give us a resultant force of 100 newtons to the right. If you're taking the higher tier exams, then you also need to be able to complete calculations where you resolve a single diagonal force into its horizontal and vertical components. This sounds really complicated, but basically all it means is that you need to turn this diagonal line into a triangle and then use whatever scale you've been given or work out from if they've given you the size of the force and you can measure the line to work out what the size of those horizontal and vertical arrows are, because the length of the arrow, of course, represents the size of that force. A force does work on an object when it moves it over a distance. And we can calculate the work done by multiplying together the force used and the distance travelled. The units for work done are joules, because work done is another type of energy, and force, of course, is measured in newtons. The distance has to be in metres, and so you may need to complete a calculation when you work out work done if your distance is given in centimetres or kilometres or something else. A joule and a newton metre are the same thing, so the conversion factor is 1 to 1. Hooke's law can be used to describe elastic objects. In other words, objects that can deform in response to a force being exerted on them and will then reform and go back to their original shape. Hooke's law says that up to their limit of proportionality, the extension of that elastic object will be directly proportional to the force that is exerted on it. What that means is that the amount that a spring or an elastic band will stretch by is directly proportional. So if we double the force, we will double the extension, or if we halve the force, we will halve the extension. The limit of proportionality is the point where that rule, that relationship, stops applying. So in other words, it's the point at which our spring will suddenly start to extend exponentially, and the spring will stretch so much that it then won't go back to its original shape. The equation connecting force, spring constant and extension is that force is found by multiplying together the spring constant and the extension. The spring constant is given in newtons per metre and extension is given in metres. Hooke's law can also be applied to objects that are squashed rather than stretched, and we use the exact same formulae, just in this instance the E stands for compression rather than for extension. A stretched object is a store of elastic potential energy, and this happens because when we stretch the object, work is done. The equation connecting elastic potential energy, spring constant and extension is that EPE is half KE squared, where the K is the spring constant and the E is the extension. Distance and displacement and speed and velocity are two pairs of quantities that students often get confused between because they seem quite similar, but the difference is that in each instance one of these is a scalar quantity that only has magnitude, whereas one of them is a vector quantity which also has a direction. So if we think about distance and displacement, distance is about how far you have gone and it doesn't take into account the direction. So if you imagine if you went on a walk and you were worried about how much effort it was going to take you, what you would care about is the distance. You would care about the number of steps you were taking. Whereas displacement is about how far you have gone in a given direction. So if you'd walked a really long way and then you were going to fly back, and so you could take the most direct route possible because you weren't having to go on particular roads and so on, then that would be thinking about the displacement. In a similar sort of way, speed is about how fast you're going, but it doesn't take into account the direction. So to calculate speed, we do distance divided by time. Whereas velocity is a vector quantity, it has a direction. So for instance, it could be the velocity to the north. And so we work it out by doing displacement divided by time. And that does also mean that velocity can have a negative value. So for instance, if I've defined velocity as being to the north, if I'm moving due south, then my velocity will be a minus number. To calculate speed, we do distance divided by time. As we've just established, velocity is a vector quantity and it can be defined as speed in a given direction. That means that velocity changes if speed changes, but it also changes if direction changes. So for instance, if an object is following a circular path, so for instance, if you were driving around a racetrack, then although you might have a constant speed, your velocity would be changing. A person's speed when they walk could be affected by their age, by their terrain, so the type of surface that they're walking on, their fitness, or also by the distance travelled. So obviously if you're walking a short distance, you can maintain a faster speed than if you're walking a marathon. The typical speeds that are quoted in the physics specification for walking, running and cycling are 1.5 metres a second, 3 metres a second and 6 metres a second. In air, sound travels at a speed of 330 metres a second, and on a distance time graph, the speed is the gradient of that graph. So for instance here, if I wanted to work out the speed of this object, I could do 500 divided by 50 in order to work out what the gradient of that graph is. And also on a qualitative level, that means that if the gradient is more shallow, that object is moving more slowly. Now that remains true if the velocity of an object is changing over time. We can still calculate this from a distance time graph by using the gradient, but now we would need to draw a tangent. Remember, a tangent is a straight line that touches the curve in one place, and you then just treat that tangent as if it was the original graph, and so you work out the gradient by doing the change in the y-axis, which is the distance, divided by the change in the x-axis, which is the time. To calculate acceleration from change in velocity over time, we do change in velocity divided by time. And when we talk about change in velocity, we mean the final velocity minus the initial velocity. So you could also express this in this form. Now, if you don't have time, but you do have distance, we can use a different equation. So we can say that final velocity squared minus initial velocity squared is equal to 2 times the acceleration times by the distance. And of course, you could rearrange that to have acceleration on its own. Acceleration is measured in meters per second squared. So the seconds is squared, not the whole thing. And the acceleration of an object can be calculated from a velocity time graph, again by looking at the gradient. When looking at a VT graph, the area under the graph represents the displacement of the object. So if an object is moving at a constant velocity and we have a horizontal graph, then in that case you could use the area of a rectangle to work it out. Or if it's accelerating at a constant acceleration and so we have a diagonal graph, then you could use the area of a triangle to work it out. An object that's falling freely near to the Earth has an acceleration of 9.8 meters per second squared, and eventually that object will reach terminal velocity, which is the maximum velocity that it can reach, because at this point the forces acting on it are balanced. So for a falling object, it will reach terminal velocity when its weight is equally balanced by the air resistance. Newton's first law is the idea that where forces that are acting on an object are balanced, its motion will be unchanged. So if that object is stationary, it will remain stationary, it won't start moving, and if it's already moving, it will continue to move at a constant velocity. We sometimes call this uniform motion or uniform velocity. Inertia is the tendency of objects to keep doing what they're doing with respect to motion. So it's that idea that objects that are stationary will remain stationary and objects that are moving will keep moving. Newton's second law is the one that tends to be summed up in the equation F equals ma. So what this tells us is that the acceleration of an object is directly proportional, that's what this little fish sign means, directly proportional, to the resultant force acting on it. In other words, if we double the force, we will double the acceleration. And acceleration is inversely proportional to the mass of the object. So an object that is twice as heavy will only accelerate by half as much. The equation connecting these is force equals mass times acceleration. Inertial mass is a measure of how difficult it is to change the velocity of an object, and it can be found as a ratio of force divided by acceleration. And then Newton's third law is the idea that when two objects interact, the forces they exert on each other are equal and opposite. Now this may seem very trivial, but it's important to flag that when you're discussing stopping distance, we're talking about a distance. So it's not the time and it's not the force. I cannot tell you how many times I have marked an answer asking what is stopping distance and someone talks about the time taken. So stopping distance is the distance that an object or a vehicle travels before it comes to rest, and it's made up of two components, the thinking distance and the braking distance. Thinking distance is the distance that the vehicle travels during the driver's reaction time. So it's not about the time when the driver is consciously thinking, oh, there's an obstruction in the road, maybe I should press the brakes. It's the actual reaction time between when they start making that decision and when the nerve signal actually makes it to their muscles. Then braking distance is the distance that is travelled while the vehicle is under the braking force. So how far does that car go while your foot is on the brake? Human reaction times generally vary from about 0.2 to 0.9 seconds based on a number of factors such as your age and how distracted you are. In order to measure a person's reaction time, we can use the ruler drop test, and of course this is one of your required practicals for GCSE biology, so you should be very familiar with this method and able to describe it. So in order to complete the ruler drop test, you need 2 people and you also need a meter ruler. So one person holds the meter ruler with the 0 centimetre mark in line with the second person's finger and thumb. So they're making a kind of pincer and they're ready to catch the ruler. Then, without warning, the first person drops the ruler. It's important that they're not giving any warning, because if they did, then the person would be responding to their voice rather than to the ruler dropping, and we wouldn't get valid data. The second person catches the ruler, and then we measure the distance. How far did it fall before they were able to catch it? And finally, we compare that to a conversion table, which can tell us, for this particular distance, the person's reaction time was this. The first factor that can affect thinking distance is the vehicle's speed, and this is because while it won't affect the reaction time of the driver, if the vehicle is moving at a higher speed, then it will cover more distance in the amount of time that it takes for that nerve signal to go from the driver's brain to their muscles in order for them to actually hit the brakes. The other 3 factors are all things that will affect their reaction time, so whether or not the driver is tired, whether they're under the influence of drugs or alcohol, and also whether they're distracted. Braking distance again can be affected by speed, both because if the vehicle is moving faster, then it will cover more distance in the same amount of time, but also because it will require a greater distance for the vehicle to go from 70 miles an hour to 0 compared to, say, 30 miles an hour to 0. And then the braking distance can also be affected by adverse road conditions, in other words, the road surface, wet or icy weather, and here it's really important that you're specifying weather that will actually make it hard to brake. Don't just say weather because you may not get the credit for it, and also poor tyre or brake condition. So again, you need to be specifying parts of the car that will actually affect braking distance rather than just saying the condition of the car, because it's not going to make any difference if the bodywork is a little bit beaten up. When braking, work is done by the friction force, and so the kinetic energy of the vehicle is transferred into thermal energy, and therefore the brakes heat up. In order to slow down within the same distance, if you're travelling at a greater speed, you're going to require a greater braking force. And large decelerations may be particularly dangerous because the brakes may overheat and you may also lose control of the vehicle. If you're taking the higher tier papers, then you should be aware that in order to calculate momentum, you multiply the mass by the velocity. And this is one of these nice instances where if you know the equation, it gives you the units or vice versa, because in order to work out the units for momentum, we take the units for mass and the units for velocity and multiply them together to get kilograms meters per second. Conservation of momentum is the idea that within a closed system, the total amount of momentum at the start of an event will be equal to the total amount of momentum at the end of an event. Finally, if you're taking GCSE Physics, or what we often call triple science, there are a couple of other little bits about momentum that you need to know. So firstly, a change in momentum occurs when a force acts on an object that is already moving or that is capable of moving. In order to calculate the size of the force that is experienced, we work out the rate of change of momentum. So the change in momentum divided by the time. In other words, the faster that the momentum changes, the greater the force that an object will experience. We then relate these to car safety, and these are 2 questions that come up quite frequently, and quite often people lose quite a lot of marks because they just start talking about car safety in terms of, oh, an airbag is soft so it doesn't hurt your face as much, or a seatbelt stops you going through the windscreen. And it's really important that you don't do this because you won't receive any credit. You need to be answering in terms of changes of momentum and forces. So first of all, let's think about airbags. The way that an airbag works is that it increases the time taken for your head to stop. If you just went face first into the steering wheel or into the dashboard, your head would stop very, very quickly. So you would go from having a lot of momentum to no momentum in a very short space of time. So because the airbag has some give in it, rather like bouncing on a trampoline rather than jumping onto a concrete floor, it takes a longer time for you to stop moving because it can deform and it can absorb some of that. So this will decrease the rate of change of momentum, and therefore this will decrease the force that is experienced by your skull. In a rather similar way, seatbelts also make that change in momentum happen more slowly. So when you have an impact and the seatbelt stops you from moving, it actually stretches slightly. So think about a seatbelt not in comparison to what would happen if there was nothing there, but in comparison to what would happen if you just had an iron bar across your chest. So because the seatbelt stretches slightly, it increases the time taken for you to stop. And so again, this decreases the rate of change of momentum. You still have the same amount of momentum at the start, and you still have the same amount of momentum at the end, but because it's taken longer for that change to happen, the rate of change is lower. And that therefore means that the force that's experienced on your rib cage is also lower, and so there's a lower chance of injury to you. Thank you very much for watching, and hopefully you found that a useful summary of all of the content for Unit 5 of AQA GCSE Physics. If you did find it useful, then let me know in the comments below, and don't forget to like and subscribe for more GCSE Physics videos coming soon.